present some results that on the approach of integrability to compute correlation functions in for the integrable supersymmetric gauge theory. Some of this, I mean, there is a long story about the applications of integrability to compute correlation functions. I'm going to talk about a recent work to apply these techniques for a new class of supersymmetric gauge theory, which have less supersymmetry than n equals 4 super-Young Mills theory, where the techniques were initially developed. Work that we have done last year with my collaborators Gwenaël Ferrando, Gabriel Lefundes, my student, with Shota Komatsu. And also this work is based on some previous work that we have done with Ivan Kostov and Valentina Petkova on computation of a particular correlation, 4-point correlation function in n equals 4 super-Young Mills. To the next slide, but okay. Thanks. So the motivation is, as I was saying, the integrability of planar n equals 4 super-Young Mills theory opened the possibility to study strongly coupled gauge theories. Using also inspiration from duality with strings. Under the correspondence between, there is a dictionary between the objects in the n equals 4 super-Young Mills theory and integrable superspin chains. So under this dictionary, the local gauge invariant operators, which can be represented as I will consider only single traces here, single traces of products of fundamental fields of the theory. So here Z and X are some particular fields that I will specify a little bit later. So these traces can be mapped to the state of a spin chain where an operator Z is mapped, for example, to a spin up, and the operator X is mapped to a spin down. So we have a mapping from between a particular gauge invariant operator in n equals 4 super-Young Mills and a state of an integrable spin chain in 1+1 dimension. A lot is known about the spectrum of this of the anomalous dimensions of these operators, and the correlation functions can also be computed with techniques inspired from the integrable two-dimensional field theories. In particular, the notion of non-local form factors will be important, and one of the motivations to develop these techniques is to be able to compute Feynman integrals using these techniques based on symmetries and integrability-based techniques. So the outline of my talk will be, I will start with a review of the ADS CFT spin chain and the dictionary between the spin chains and the gauge theory. Then I will mention, I will specify the way how to compute correlation functions in n equals 4 super-Young Mills, and how this geometric decomposition in terms of non-local form factor works. Then I introduce an object which is a particular building block of the correlation functions, which can be computed exactly as a Fredholm determinant. Then I switched to the subject of I mean, the main result of our work, which is how to apply these techniques inspired from n=4 super-Young Mills to an orbifold version of n=4 super-Young Mills, which has reduced supersymmetry and which is a ZK orbifold of the original theory. So there are results which were obtained from supersymmetric localization for twisted BPS fields in this theory, and we were able to reproduce these results using the techniques of integrability. To introduce the dictionary and the notation, the terminology, in the at weak coupling, so we're in the planar limit of n=4 super-Young Mills, where the coupling constant is the 't Hooft coupling constant, which is this part here, G square Young Mills times the number of colors. So I will use a notation for the coupling constant, which is specified here. So it's weak coupling. The spin chain description is just a supersymmetric generalization of the isotropic Heisenberg spin chain. And then the deformation of the isotropic Heisenberg spin chain is controlled by this coupling constant. So at higher loops, we'll have more and more longer and longer range of interaction on the spin chain. The spin state, so I said it's a generalization with more fields of isotropic Heisenberg. The spin states correspond to fundamental fields in the gauge theory. So one has of course, the gauge fields, and then a set of 6 real scalars, which are mixed into each other by SO6. And then 4 copies of fermions, which are also mixed, turned into each other by the same group. Well, they form a spinor representation of SO6. So the fields I was mentioning before, Z and X, are complex combination of some of the fields, real bosonic fields. So the whole symmetry algebra of the theory is given by, well, there is a bosonic symmetry, which is this R symmetry SO6. There is also the conformal symmetry. The theory is conformal, so there is the conformal group is acting as well on the fields. And there is, of course, supersymmetry, and the whole symmetry group is given by PSU 2,2/4, which is also an isometry of the string background, which is dual to the theory, which is ADS5 cross S5. Again, in the language of the spin chain, the vacuum state is associated to BPS, half BPS operators. For example, the trace of Z to the power L is associated to the ferromagnetic vacuum of the Heisenberg model. The excitations above this vacuum are the so-called magnons, which have different flavors, which are described by a product of 2 PSU22 algebras that I will call one left and the other right. And these quasi-particles have a scattering matrix they have factorized scattering, and they scatter with the Bizart scattering matrix. And then the rotating string solutions in the string theory will correspond to some particular solutions for the spin chains, which are called Sutherland solutions, which are close to solution which are close to the ferromagnetic vacuum. As I was saying, the spectrum of anomalous dimension of the theory was formulated. The problem of finding the spectrum was formulated in the integrability language by an object which is called the quantum spectral curve. The problem of computing correlation functions in this theory is still not completely settled. For the two or three point functions, they are determined by conformal invariance up to some data that is that can be obtained from integrability. So part of what comes from the spectrum of the integrable spin chain is associated to the spectrum of anomalous dimensions of the operators of the theory. These are also they are spin chain energies in the spin chain language. So this is what the quantum spectral curve computes. And for the 3-point functions, the space-time dependence is, of course, established by this dependence on the anomalous dimensions, and the only part that remains, which is not determined by conformal invariance, is this structure constant, which depends in general on the coupling constant, except for the case of correlators of BPS operators, where these structure constants do not depend on the coupling constant. For this structure constants, what we have are three sets of initial data, which would be what are the three different operators that we want to compute. What are their charges. So once we give these charges, what are the let's say beta states which are associated to these three spin chains, which are connected by this string vertex-like interaction. So this is what we have to determine in our computation. So at weak coupling, it's in the spin chain language, this structure constant will be given by contraction of a weak contractions of different insertions of the fields of the three gauge invariant fields. So it just reduces to a combinatorial problem, but in general, when we start to introduce the interaction on the spin chain, it's becoming more and more complicated to treat, to describe microscopically. So what can be used efficiently is to impose the symmetries of the problem. So that proved to be a efficient way to compute the spectrum, the scattering matrix, and this proves to be also an efficient way to compute the correlation functions. So the idea to how to impose the symmetry is to have a decomposition of this pair of pans. So we represent the 3-point function as a pair of pans. Each of the insertions of the operator will be one of these spin chains, and each of the spin chains have some excitations, some magnon excitations, which are associated to them. A representation which was inspired by the spin chain decomposition was to, but also by the string decomposition, is to take this object and cut it into, so you have a pair of pans, you can cut it into two hexagons along these 3 lines, and then when you are cutting these 3 lines, you will split the collection of magnons in all the different ways between the 2 hexagons. So that was made by Basso, Komatsu, and Vieira, as I was saying, was inspired from the spin chain computation at weak coupling, was to compute the asymptotic part, when the 3 lengths are large, will be given by the sum of two amplitudes which are related to the 2 hexagons, summed over all the possible distributions of this of the magnons between the 2 hexagons. Dressed with some transition factors that are associated with magnons transitioning from one hexagon to the other through the three different bridges that over which we have cut the hexagons. This is what I called the asymptotic part of the hexagon, but then if you want to consider arbitrary lengths of the spin chains, you want also to consider all the virtual particle circulating in between the 2 hexagons. So each of these lines will be then will correspond to the insertion of a complete system of intermediate states. So you will have to sum over all the magnons that can flow between the 2 hexagons. The particles will be exponentially surprised if these bridges will have big lengths, large lengths. If you have any questions about this decomposition, please. Means so you can, for example, you can insert Konishi operators here, so that's length 2 for certain representatives. So then you have to, I mean, this approximation is not true anymore. So you will have to sum over everything that flows in the intermediate channel. So the finite size corrections will be important. So yeah, I will mention that a little bit later. The question is, of course, how to determine this hexagon weights. So that was a problem that was solved in the paper from 2015 by Basso, Komatsu, and Vieira. So these hexagons are like infinite volume form factor of a twist operator. which introduces, which introduces the fact of curvature in the middle of the hexagon. In fact, you can see it as a, so you have three different incoming states that are joining to each other by this by this object, which so if you want to make a pair of pants from a piece of paper, you have to introduce some defect of curvature, because otherwise you cannot glue them properly. So this is, you can compare this kind of form factor with the local form factors, where you have some just a flat strip of paper. You introduce some excited state, then introduce some propagate, introduce some operator, and then project it on the vacuum or a different state. So this would be local form factor operator. And in an integrable 2D field theory, relativistic, you can imagine moving magnons from one side to another of the rectangle by making a shift of the rapidities by I pi over 2. So this will transform a physical particle into virtual particles. So this kind of transformation is also implemented in this hexagon. Once you introduce, all the constraints that this kind of object should obey. What's on? There is a set of axioms that form factors should obey, and the solution, there is a unique solution of this form factor axiom that was obtained by Basso, Komatsu, and Vieira, and this looks like some scalar part, which is a function of the rapidities that was explicitly determined, and then there is some dependence on the flavors of the magnons, which is essentially given by the Bizart's S matrix. So the left and right flavor indices have to be matched in a particular way that's given by the Bizart S matrix. So that I explain you how to get a 3-point function from hexagons, but this method can also be applied for higher point functions. In principle, you can imagine if you have a four-point function in a CFT, you would like to decompose it in a OPE decomposition. So you cut this object in the middle, and then you decompose it in two pairs of pants. But in fact, there is a more efficient way to do a hexagon decomposition of the 4-point function, which was proposed by Fleury, Komatsu, and Didina Serban in 2016. And this is represented in in this picture. So it's if you imagine this surface as a sphere with 4 insertions, then this decomposition is essentially a triangulation of the sphere with the four insertions. Decomposition, and then if you want to compute your 4-point function, you have to compute, to insert all the virtual particles that you have on the cuts. In general, this is not easy to do technically, but there is a case where this resummation was done. So this is explain it in the. I will explain it next. So it can be done when you only have one of these cuts to sum over. When you have several cuts, there are the interactions between different magnons for different cuts that are more complicated to compute, and in particular when you want to close your hexagon into a leg, then there are particular problems that appear. There are you can get divergences from the magnons that are wrapping one leg of the pants. So that is one of the problems that was not completely solved. There are the case where I mean the general structure was conjecture in a paper in 2002 by Basso, Gergudis, and Clemenciu-Suero. So that would be a way to recover the TBA description of the spectrum starting from the hexagon construction. One way to avoid this divergence is coming from the magnons that wrap around the leg of the pants is to consider insertion of VPS operators, because then there are supersymmetric cancellations which cancel this the divergences, which make the divergences disappear. That happens. So imagine that we are taking one 4-point function with only BPS operators. Taking a 3-point function of BPS operator is trivial because the result does not depend on the coupling constant. So the answer is known from zero coupling. As I was saying, you can consider a particularly simple case where you engineer a 4-point function, taking operators which are large, such that you build some bridges of very large length, where these virtual particles cannot. I mean, they are suppressed when they cross one of these bridges. So then you effectively separate your sphere. You cut it in two, and you get two pieces of two octagonal pieces. So each of them is a gluing of two hexagons through one virtual line. Mirror line, and that gives you a factorization of the of your object into two octagonal contributions. So because of conformal invariance, this object depends only on the two cross ratios that can be parameterized in terms of some of variables z and z bar. And of course, the dependence on the there is an extra dependence of the 4-point function given by this overall factor. So that construction, that configuration was suggested by Coronado in 2018, and it happens that this object, the octagon, the contribution of this half of the sphere is can be computed exactly, and it is a Fredholm determinant. And since then, this object was analyzed, so that different kinematical limits were analyzed. There is some resurgent analysis that you can perform on the object because it's, I mean, it's explicitly known. So, and also this object has some combinatorial properties that were discovered and analyzed by Gregory Korczewski last year. To explain a little bit how this object is computed, what is the structure that makes it exactly solvable. So I will consider now the case of these two hexagons. Now they can be separated. I can put any number of bridges in the middle, so it doesn't change very much. You can also compute this exactly. So each one of these hexagons will emit magnons and the other will absorb them. So we have to compute the sums over all possible all possible numbers of virtual magnons crossing from one side to the other. So the structure of the octagon, which depends on the space-time cross ratio, and there are some cross ratios in the R space, in the space associated with the sphere, if you want. So this will be a sum over all the number of mirror magnons crossing between the two hexagons. There is a part which contains a relatively simple part which contains the cross ratios, and then you have some integral which depend only on ZZ bar. And this integral here so will be a sum over the rapidities, the momenta, if you want, of the mirror magnons. There is some measure of integration, one particle measure which contains the number of, the L here is the same as this one here. So it contains the dependence on the bridge length. It contains the dependence on the cross ratios and also the other kinematical dependencies. And then there is a part here which is universal, only contains a function of rapidities. Well, there are some indices which correspond to bound states of this mirror magnons, and then so this interaction can be represented as a Pfaffian of some variables that are defined in terms of the rapidity variable. So the details are not extremely important, but yeah, they are coming from the definition of the problem. This object here can be written as a Pfaffian. Implies that this whole representation here can be written as a Fredholm Pfaffian. And then by some manipulation, it can be written as a Fredholm determinant, as the square root of a Fredholm determinant. So in the end, the octagon can be written as well. There is some subtleties of some subtleties that implies that you have to sum to average over two particular dressing of this kernel, but I am not going to give details here. In any case, be a Fredholm determinant for the determinant of a half infinite matrix, which whose elements are given here. This object contains which is given in terms of Bessel functions, and then some weight. This object here, this chi, which contains the dependence on the kinematics. So it depends via this parametrization here of the cross ratios with some angles and some with some angles. Chi of t will contains the information related to which specifies our particular problem, and this kind of object appears in many other places in many other objects in n equals 4 super-Yang-Mills. And the only thing that changes will be this weight here, this function chi of t. The structure of in terms of the Bessel function stays the same. This object showed up in some expression for the 2 and 3 point function in the quiver n equals 2 super-Yang-Mills theory. So the question is, okay, this comes from integrability. This appears also in the n equals 2 super-Yang-Mills theory, and there it appeared first through localization computation. So the question is, okay, is it okay? So let's switch now to the n equals 2 theory and see what how it appears and how can we find it using integrability techniques. N equals 2 quiver theory. It's a version of n equals 4 super-Yang-Mills that is twisted by ZK twist. So suppose that we have a diagonal matrix which is block diagonal with blocks of the size of the gauge group. I mean, the element components of a gauge group. The gauge group is now SUNC to the power k, and all the fields, the gauge fields, are k nc times k nc matrices, and different fields have different behavior under the action of the twist. The gauge fields are invariant under the twist, while the x, y, and z, so the gauge fields and the field that I call z are gauge invariant, and the other twist invariance, and the other have are sent into, are multiplied by a factor or root of unity, kth root of unity when the twist is applied to them. The supersymmetry is reduced now from PSU to 2/4 to SU to Komatsu times SU2, and the magnons are also twisted. So the left component of the magnon is not touched. This will be SU2, 2 here, and the other, SU2/2 will be unaffected by this left twist, and the other part will be twisted, which means that SU2, PSU22 will be twisted to SU2 times SU2. So this theory is also expected to be integrable when the k different gauge groups have the same coupling constant. This theory is uh, um, described by a matrix model in the supersymmetric. I mean, the supersymmetric the BPS sector is correlation functions can be obtained from supersymmetric localization using a matrix model description that was given by Pastun. So different quantities were computed with this supersymmetric localization method. And they are given in terms of this octagon kernel that I have shown earlier. Okay, so now let's look at the correlation functions for the operators, half BPS operators. So the same representation as before. If we take the trace of the z to the power L fields without insertion of a twist, this would be the untwisted sector. Then one can have a twisted sector when we insert the power of this twist operator here inside the trace. So the dimension of these fields are still protected by the symmetry. They do not receive corrections. This computed from the matrix model by Beccaria and collaborators and by the groups that works in Torino. Perturbative computations were these results were checked by perturbative computations by Galvagno and Preti. So essentially, if you are computing correlation functions of operators from the untwisted sector, you will get the same result as you will get in n equals 4 super-Mills. There is no dependence on the coupling constant. While for alpha, for the sectors, the twisted sectors, you will get the result of for zero twist multiplied by a ratio of Fredholm determinants, which are associated to this octagon kernel with an index L, which is related to the length of the operator here that we compute, differing by 2 units. So I will represent this kind of correlation function by a cylinder with a twist inserted along the cylinder. Yes. Chi function. The chi function will be this object is a particular value of this. So psi will be equal to 0. Is equal to, well, I don't remember the exact values of these different parameters, but it's a particular value of this function. The value of the twist is enters just through this number here, which is sine square of the twist, essentially. Questions about this? That's about the 2-point function, and now the 3-point function, which is an object which is a little bit more interesting from the point of view of integrability. It was also computed in 22 uh, by the group in Torino. So their result can be expressed as following. If one writes down the normalized 3-point function, so the 3-point function divided by the norm, again you get the contribution you expect from conformal invariance, and then you have a structure constant which depends on the three twists that you insert, but the three twists have to be conserved. The sum of the two twists have to be equal to the third one, modulo k, and the configuration has to be extremal because you have to have the number of fields here have to be equal to the number of these two fields here in order to have charge conservation in the R sector. So P has to be equal to K plus L. That's the result that was obtained by localization. Okay, it was written a little bit differently, so we have a different. I mean, an expression which is a little bit more symmetric. Yeah. So that's what I'm going to explain now. How we are getting this from this hexagon approach. So the structure of this of the structure constant is such that it factorizes in three in three factors which are completely independent and which are associated to each of the operator insertions, and these particular factors are given again in terms of the octagon answer as determinant divided by square root of product of two determinants with slightly shifted values of L. So this is something that we can. Okay, so I will discuss the origin of these different factors. Okay, so now I will explain our computation from hexagon decomposition with twist insertions. So now we are writing this hexagons with all the virtual magnons and two twists inserted before gluing back the hexagons. So we can see that there are different contributions from different configuration of magnons that will reproduce these different factors. So although they seem, they look very similar in this hexagon decomposition. They have different origins. For example, this factor here, this determinant, will looks very much like the octagon. We'll have there is one contribution which comes from this bridge here, decorated with magnon. One which comes from here. So two contributions of this type come from these two bridges, but there is another one which looks exactly the same, but there is no bridge which has this length here, this length Kp. So this contribution comes from a contact term that implies three different magnons. And also the square roots here, they come from contact terms which are associated to pairs of magnons on different sides. So I was telling you earlier that this hexagon approach has a complication which comes from divergences and possible singularities. These are originating in these contact terms, and this is a simple setting where we are able to look systematically at this how these contact terms are appearing. Moreover, there is no divergence related to them because the divergence is coming with the correction for the anomalous. I mean, with the anomalous dimensions for the three operators insertions. And as I was saying before, these are BPS operators, and their anomalous dimension is zero, so there is no singular term, but still there are finite contact terms which manifest themselves into these wrapping corrections. So this is a kind of lucky case where we can understand how things work. So how much time do I have? Probably 10 minutes, or it's going to be a little bit more technical, but I will try to explain how to handle this singularity. I mean, these possible singularities that we have in this sum over magnons. So we follow a procedure that was suggested by Benjamin Basso, which is to use a finite volume regularization. In fact, these singularities are coming from the fact that the legs of the pans have infinite volume, half infinite volume. So in order to regulate these singularities, we have to introduce some finite volume regularization. So he was using 4-point function to regularize the 3-point function, but here we are closing, in fact. So we are taking the square of the 3-point function by multiplying two structure constants, and then so glue each of this pair of legs together into some finite volume configuration. And we'll take this length here to gain back to infinity and see what we get in the limit. So we glue this pair of pans into two torus, and then with the twist insertions, and then we cut again these two torus into another pair of pans, but this time virtual pair of pans, where we have the virtual magnons circulating in these three holes. So doing this this procedure, we can now, when we're cutting open these lines, we'll start to reveal the virtual magnons that are distributed there. So we'll have three different type of virtual magnons of the three different colors. At the end, we cut again this pair of pans into hexagons. So now we are using the prescription of, writing the 3-point function as a decomposition in hexagon and distributing the magnons in all the possible ways between the two between the four hexagons. This kind of decomposition, we are able to see that for the wrapping contribution, the only terms that survive have either all the magnons on one side of the, all the magnons on one side of the the lower hexagon, and the other pairs on the upper hexagon. And this provides us with a representation for the wrapping contribution at all loop, which will be given in terms of, okay, so we have again this integrals, multiple integrals, and a sum over the bound states of an object which is a square of the products of the S matrices that define the scattering of these magnons, and then yes. Yeah, the ADS5 matrix, but you see, I have 2 times these blocks. So it's a kind of torus distribution, and then I have to send the rapidities to coinciding points and taking the derivative over one of the set of rapidities, and inserting the twist. If I don't insert the twist, this result will be 0 because of the super trace. So, okay, it looks a bit complicated, but still is a closed form. We know what this object here should give, because we know that the square of this object should give 1 over these products of determinants, because we know should get from the wrapping contributions, the term that I was analyzing, we should get this square root here. I think a bit complicated to evaluate this the sum over all the bound states and this the super traces and so on, but there some analytical miracles occur that make it possible to get this this expression here in terms of Fredholm determinant. So still we don't have a complete proof that, we don't have a proof, general proof that this object here becomes the product of determinants, but we have checked on expressions with up to 3 magnons that this is true. And even more subtle is to show that the contact term of 3 different magnons reproduces this bridge-like term here. So, for example, there is this is one of the typical contribution that reproduces the one magnon contribution from here. I think I will not go into more technical explanations here, except if somebody asks me about the details of the computation. So, we to conclude, we showed that we can get the result obtained by localization techniques in terms also from integrability by summing over. So there is a possibility to connect the two approaches, which are complementary, because the localization approach gives finite NC results. So we can imagine comparing, so doing 1 over NC corrections in the integrability approach. Also, the question is, there are results by the group of Eli Pomoni indicating that in the case when the coupling constant for the 2 gauge groups are different, the theory might be still integrable. So this is a way, possible way to compare and to check that there is some integrability structure when the 2 gauge couplings are different. From the integrability approach point of view, this one of the outcomes is to have this all magnon expression for the wrapping corrections. And we hope that this will also help to understand the systematically wrapping corrections and the TBA, how the TBA appears from the hexagon approach, in particular considering twists that break supersymmetry. It would be interesting to, there is a recent work setting up this integrability procedure for non-BPS operator in the orbifold theory. So it would be useful to check this against perturbative computations, because now the localization techniques are not available anymore. So yeah, and okay. Thank you for your attention.